This video goes over the change of base identity for logarithms. So far we've used logs to solve exponential and logarithmic equations. We've done a little bit of graphing, but there's one type of question that we have avoided. We have avoided solving things like this: log 263 or log 265. Calculators work in base 10, so we can't just use our calculator to do that. So let's take a look here. So we would do, if we had this solution, 2 to the 63 equals y, the first thing we would do is change this into exponential form. Then we would take the log of both sides, which allows us to bring the y down. And then we divide both sides by log 2. So log 63 divide by log 2, which then using a calculator will give us about 5.98. So we notice that log 2 of 63 is log 63 over log 2. But we want to know that if this works in every case. So let's take a look at the general case and prove that it is true all the time. So log base b of x is equal to log of x over log base b. So let's let log base b of x equal y. Then we have b to the y equals x. We can take the log of both sides, which allows us to bring down the exponent. And then we divide both sides by log b. Oops, divide both sides by log b. So therefore, it is true all the time. The change of base formula states that y does equal log x over log b, or it's the log of the answer over the log of the base. So now what does that really mean? So let's take a look at some examples. So the first one is we're going to use our calculators to evaluate log base 3 of 23. So I'm going to use my change of base formula to change, really I'm changing log base 3 into log base 10. I know that it's the log of my argument over the log of my base, which is approximately 2.86, because I can evaluate that using my calculator. So now I want to show the different property. Log base t of b is equal to 1 over log base b of t. So let's start with our left side. We've got log base t of b. Using my change of base formula, I know that I can rewrite this as the log of my answer, or my argument, over the log of my base. Now, the next thing that I could do is I'm going to take the reciprocal of this. So I'm going to do 1 over log base b of log t. And when I rewrite this as a triple-decker fraction, I want to flip those two. So here, I'm just trying to play around so that I've got 1 over on this side. So I'm changing my double-decker fraction into a triple-decker fraction. The last thing that I'm going to do is use the change of base formula again, right here. And I know that log t over b, this is my answer, my argument, and this one is my base. So that means I can change log t over log b into log base b of t using my change of base formula backwards. Yeah. The next one, I guess we should say, to make this a little bit more formal, Should have our right side here, which is 1 over log base b of t. So therefore my left side happens to be equal to my right side. Okay, so let's take a look at this example here. Show that 1 over log base 3 of a plus 1 over log base 4 of a is equal to 1 over log base 12. So let's start left side, right side. Right side is 1 over log base 12 of a. I'm going to leave that alone and see if I can change these two into that right-hand side. So let's see, 1 over log base 4 of a. Now, I can actually use the property that I proved above, so this one. So log base t of b is 1 over log base b of t. So I can rewrite my left side. So in my fraction, the base of my logarithm is going to become the argument, and my argument of my logarithm is going to become my base. So I have log base a of 3 plus log base a of 4. I know that when two logarithms are separated by an addition sign, I can multiply those arguments together. So this gives me log base a of 12. Now, using this property again, my base of my logarithm is going to become the argument when I put it on the denominator. So this is a, and my argument is going to become the base of my logarithm. So therefore, my left side is equal to my right side. Let's look at one more example here. And this one I've kind of got an equation, something that's a little bit more complex. So if a squared plus b squared equals 14ab, that's the first thing I know, a and b are greater than 0, I'm trying to show that log of a plus b divided by 4 is equal to 1/2 times log a plus log b. So the first thing that I'm going to do is I'm going to play around with a couple things. So let's start with this. So a squared plus b squared equals 14ab. Now I can't really do much with this. I probably want to see if I can factor the left-hand side, but I can't right now. So in order to be able to factor it, I'm going to change it into a perfect square trinomial. Now, because I did that on the left-hand side, added that 2ab, I also have to add it on the right-hand side. So I'm changing to a perfect square trinomial. Okay, so this is going to let me factor it as a plus b all squared equals 16ab. The only reason I added it on the right-hand side is to make sure that my expression didn't change. So now, if I divide by both sides by 16, now I have a plus b over 16 squared, a plus b squared over 16 equals ab. So kind of interesting here, if I look at this expression here, it looks like I have almost the square root. So let's see if I can make that happen. So I'm going to change this into a plus b over 4 all squared. So my expressions are equivalent. And now, all of a sudden, I have that a plus b over 4 that I was looking for in the first place. So then I want a plus b over 4 by itself. So I'm going to take the square root of both sides, which means that I've got a plus b over 4 equals the square root of ab. So using that relationship, I'll do my left side, right side table here. So my right-hand side is 1/2 log A plus log B. I can change this one here a little bit. So I could change this to 1/2 log A times B. Maybe you can see where I'm going with this. And then that 1/2 is a coefficient in front. So I can actually bring that up to be an exponent. So that's kind of interesting. So now I'm going to start with my left side. So I've got log A plus B over 4. But I already did this. I used the expression that I was given to create a replacement for that argument. So now I've got log of AB to the 1/2, which means that my left side is equal to my right side. So the proofs are kind of interesting. You can use some of the properties of logs to manipulate expressions to show that they are true. Really, the change of base formula allows you to take a base, for example, log 2 of 25, and I can evaluate this by putting the log of my answer, so 25, over the log of my base. Evaluating this will actually give me the answer to this, which is the short way instead of always changing everything into exponential form. In this case, that would work as well. So I would say log 2 of 25 equals y. 2 to the y equals 25. I would take the log of both sides, and then I would end up with y equals log 25 divided by log 2. The change of base identity just means that you can use that formula right away or that property right away without having to go through the whole thing. So some interesting algebra involving logarithms.